Hello, and welcome to Hopkins at Home. I'm John Abraham, and this week we'll be talking about entanglement. Um, so, what will we be discussing? First, wave functions. I've kind of held off on that. The superposition of two states or two particles, to be more correct. Entanglement, what we mean by it, through an example, the EPR paradox, which is it's interesting how that really was from 1935, and it highlighted something that took many decades to really flesh out. And now it's important because what it fleshed out showed a way to really advance measurement. Bell's inequality, one specific test of Bell's inequality. These tests continue to this day, and entanglement and measurement. So wave functions. So you've probably heard of the Schrodinger equation. Here it is. It is a differential equation. So what that means, it's an equation which includes the function and its derivative or derivatives. And it's a second order differential equation because it has the second derivative, spatial derivative. So this is a derivative with respect to space. That's a derivative with respect to time. H bar we're familiar with. That's reduced Planck's constant. There's the mass of the particle. And to solve the equation, you need to know the potential energy. But for our purposes, we don't need that. What we're really getting to is that what you get out of this equation is the wave function, which in this case, it's a spatial function, and it describes the probability of finding the particle in a specific place. So this is some diagrams I took out of the classic Introduction to Quantum Mechanics textbook for undergrads by Griffiths. And so here you have an example wave function. Now the wave function is normalized. So that means if you integrate, if you add up all of these pieces of it, the square of it, that equals 1. So, because you got to find the particle somewhere. Now, A is significant because that's the most likely place to find the particle. B is significant because the particle's not there. This little element dx is like, that's the differential. You know, you add up all these differentials. That's the differential probability of finding the particle here. So this is before a measurement's taken. Once you take a measurement, well, you know where the particle is. And in this case, the particle was at C. So this caused people lots of consternation when it was originally introduced, because now you're saying that what we're really describing reality with is this thing called a wave function, which gives the probability of finding a particle somewhere. You know, and until you make a measurement, it's not really clear where it is. It's somewhere, described by this wave function, which is a very counterintuitive way of thinking of reality. You know, that's not how we go about things in our daily lives. So this is a bit of a jump. You can have a superposition of states. So say you have two spins, an electron and another electron, or even just an electron by itself. It can be in a superposition of states. So what that means in this case, say we have a spin up or a spin down, that there's a certain probability that the first particle is spin down or spin up, and the probability that the other particle will spin up or spin down. And then this is a wave function itself made up of littler wave functions. And this is how you would describe that situation. So if the particles travel to separate detectors and one's measured spin up, then the other one's going to be spin down according to this wave function. The EPR paradox and Bell's inequality explores the physics of the situation. And you need superposition of states to have entanglement, but, and this is kind of a technical point, it's not the same thing. Those are distinct things because you can have a superposition of states where it's clear what particles in what kind of state. But this is a unique kind of superposition, and the spin singlet is very kind of meaningful and significant because it allows for entanglement. So here we have our wave function, and this is the situation that sets up the question that we'll take up for the next 15, 20 minutes. You have a source of two entangled particles, A and B, and you take a measurement of A, of its spin, you find it spin up. You take a measurement of B, it's got to be spin down. So that's one outcome. The other outcome is the opposite of that, where A was spin down and B was spin up. So why is this interesting? Why is this a paradox? Well, how in the world is this being coordinated? How does your measurement at A have any relationship to your measurement of B when they're separated by space? So you might notice, and I haven't discussed relativity at all, but a basic tenet of relativity, and this has been tested many times, is the speed of light is constant. So even if I was on an airplane and I shot a beam of light, the speed of light, if you measure that, is the same, measured by me on the airplane or someone on Earth. So that means that it takes time for signals to travel, but the speed of light doesn't come into this. So what then that questions is the issue of locality, because there's a connection between these two particles, and there's a connection and a relationship between these two measurements. But what's not allowed is some kind of time delay or coordination. And so Einstein, Podolsky, and Rosen wrote a paper. It's somewhat readable. And they highlighted that something has to give. You know, either quantum mechanics is not a complete description of reality, and there's some type of extra part we need to add, or there's just something we fundamentally don't understand about how the world works. That was in 1935. 30 years later, about John Stuart Bell, pictured here, came up with a way to test this. So he said, let's say there's some missing variable in quantum mechanics. There's something missing with our wave function. And let's just group all of it together and call it lambda. And so that means, you know, same situation. We have these two particles. They're both being measured in different places. And our new wave function still has the same result. It's either plus or minus 1, or it's plus or minus 1. So right now we're going to go through his derivation. I've been hesitant Oh, how much? Sorry, before I dive into this, there's a question. How much space between the two particles? Well, in this thought experiment, it could be, a few centimeters between your two measurements. It could be the ends of the earth. It could be across the solar system. It's not specified. And there have been tests of Bell's inequality where, it's done in a lab on an optical table. And there have been tests of it where you'll have the particles separated between labs. Those are some of the more exciting and recent ones where they'll do tests of Bell's inequality like across a campus, which is pretty cool. So I've been hesitant to do any derivations, but I thought, hey, this is the last class. Let's have some fun. Let's try and do a derivation. I'll put myself on the spot. And there's value in derivations because it helps you understand things, but sometimes you just get lost in the mechanics of doing things. So let's see how it goes. So here's our first little bit that we need to know, that this is the outcome of measurement A on particle A, and the outcome that we see at B over here, if we're talking about A. And we know, okay, there's a question. What determines if two particles are entangled or not? That's a good question. It has to do with the preparation of the particles. So in this example, there's one example is a decay of a particle into, say, an electron and a positron, which is a positron's like a positive electron. Those two things are entangled. The way that this experiment's typically done is you take blue light, take a blue photon, and you pass it through a special crystal that does down conversion. So it takes that blue photon and it turns it into two red photons. So there's conservation of energy because the red photon is lower energy than the blue photon. And the spin, or rather not the spin, the angular momentum of those two photons are entangled to conserve angular momentum. So it's in the preparation that makes particles entangled. And that's a challenge, how to entangle particles. Those are the two most obvious ways that particles are entangled. So the first bit is that we can change the result at A with regards to A into the result at B with regards to A. Well, they're equal by a minus sign. And that makes sense because if this is plus, that's minus. This is minus, that's plus. And we remember that this is the probability distribution for lambda. This is also normalized. So if we take the integral of that, if we add up all the little differential probabilities for our lambda, that's going to equal to 1. So we start with the probability for the outcome of A and B. And then that's just an integral with our rho of lambda and the two wave functions. Well, we can simplify this based off of this expression that it's now minus this whole thing, where now we have the result at A with regards to A and the result at A with regards to B. Bell's big thing was, let's add another measurement, C. So we're not just measuring one polarization, but another polarization as well in the case of the up conversion, or rather down conversion that I was mentioning. So now we want to take the difference of these two probabilities. And here's the expression. And we know that this probability is normalized. So then what we do is we take this term out here. And so then we have a 1 there. And then since we know that psi sub a of b lambda squared is 2, we put the square of it here, and then we took one of those out. And so then we're left with 1 minus psi sub a b lambda times psi sub a c lambda, and this thing on the outside. So there are two other things that we know. We know that the measurement with at A with respect to A and then B, that product is bounded. It has to be less than 1 and it has to be greater than minus 1 because of how we constructed, we're measuring the spin up or spin down. It could have some angle, and that's why it's between +1 and -1. And so then we also know that this product has to be greater than 0. So what we can now do is we can take that expression that we had arrived to on the previous page, and we can make a statement about equality. That this one, the difference of these probabilities, has to be less than the integral of that. And what that results in is the difference in these probabilities has to be less than 1, because we know the integral of rho of lambda is 1. And then this is the probability at B and C. So now we have an inequality. And that's Bell's inequality, that the probability of your measurement of A and B subtracted from the probability of the measurement of A and C has to be less than or equal to 1 plus the probability of the measurement BC. So now it gives you a test whether or not you need hidden variables, whether or not quantum mechanics is complete. And so that was 1964. And right from the start, people tried to measure this. And it wasn't until 1982, about 20 years later, that there was an actual measurement taken of it that was good. So here they use the source that I described, where you have the polarization of the light is correlated or entangled rather. And you have 2 photons coming out. These are polarizing beam splitters. So it means they pass light of a specific polarization here, and this is a detector. And then light of a different polarization gets passed here. And similarly on this side. Is there an application for this? You'll see there is. This is quantum sensing. There has to be. Now you have your counting electronics about whether you saw something here, just there, here, and then the coincidences. And cutting to the chase, the prediction for quantum mechanics was, for this setup and taking in their experimental uncertainty, that they should measure 2.7 for the probability BC +1. And as you see, they measured that essentially. And, it's a very precise and a very accurate measurement. And you see here, they change the angle of the polarometers. And this dotted line is the prediction from quantum mechanics. And that's what they measured. The dark spots are what they measured. So this was the first real confirmation that there is no hidden variables in quantum mechanics, that it's a complete description. But it's relevant for us because now there's something meaningful when we talk about entanglement. And this is where you find it applicable. So the limits of measurement. So there's something called the standard quantum limit, and it's proportional to, say you have multiple atoms, right? And you're using them for a magnetometer. That's a good example. Well, your uncertainty is going to be reduced by the square root of the number of atoms you're using for your magnetometer if there's no relationship between the magnetometer atoms. But if they're entangled, then the limit goes down much more rapidly. It goes down as the number, not the square root of the number. So if you have a bunch of entangled atoms to use for a magnetometer, that's going to be doubly sensitive, or squared. The sensitivity will be squared relative to them not being entangled. And that's why the doing measurements with entangled ensembles is so compelling of a thing to pursue. So this is data from a recent paper where what they're looking at, they were using atoms to measure the phase of an electromagnetic signal. And here you have the uncertainty from the standard quantum limit versus, and yeah, just the phase variance relative to the standard quantum limit. And now here is a log plot of the number of atoms or ions involved. And you can see for low numbers that they're able to work at that Heisenberg limit. What I did is I added another square root of n to the plot, so that if you were at the Heisenberg limit, all of your measurements, as you added more and more atoms, that the variance would go up and up and up relative to the standard quantum limit. You'd be able to measure much bigger signal. But you can see for large numbers of atoms that no one is anywhere near being able to utilize entanglement at present in a meaningful way for measurement. And so this really is like the this really is like the challenge of the current day. How can you utilize entanglement to improve our uncertainty in measurement? And no one's quite figured this out, except for 10 atoms. So I kept this brief to save time for questions. We've talked about quantum sensing in different application spaces and what it takes to be a quantum sensor and what we'd like to be able to utilize for sensing. And now I wanted to leave time for questions. I read that entanglement is being used for secure transmission of messages. Is that true? Let me think for a second. I know for certain that people are working on that. And people argue that, using quantum communication, you can have unhackable totally secure messaging. But my personal opinion is that that's kind of a moot thing to begin with, because most attacks aren't breaking encryption. It's getting someone to give up their passwords, right? For whatever reason, like you trick them or you blackmail them and you get their passwords. So, we can make that as secure as we want, but I'm not sure if there's much value in there. But to your question, yes, people are doing that. So another question, is this relevant to quantum computing? Is there a time limit for entanglement? Will it eventually stop on its own? Great question. Yes, it's very relevant for quantum computing, because you need to entangle the qubits for it to really work, for it to really scale. Is there a limit to entanglement? The problem with entanglement is once it starts interacting with the environment, that's kind of like a measurement, and the entanglement's broken. So there isn't so much a time limit as there's like an environmental limit. And the cutting edge of quantum computing and sensing to a degree is figuring out how can you protect a system of entangled bits. And that's a really challenging problem. But on its own, it shouldn't stop. Next question. Does it make sense to talk about the spin of a particle before it is measured? I think it does. I'm thinking for a second here. It makes sense to talk about it, but it might not necessarily be a defined quantity because of how things are constructed, which I think is a different thing than to say it doesn't exist or something. If you can use entanglement for secure messaging, doesn't it violate relativity? I don't think it necessarily does, because if it's just a way of securing information, you're not really carrying information that way. So that would mean that your way of protecting the information is in itself carrying information. Actually, Griffiths has a really good discussion about that, about how relativity is not violated by, it's called a superluminal relationship, this issue of entanglement. Theoretically, if you have two particles spin up and spin down, which are miles apart, how could anyone outside of laboratory conditions be able to ascertain that they were an entangled pair? That's true. But also, how could they communicate their result? So these people are miles apart, and one person measures spin up, and he knows or she knows that the other person must have seen something else, but there's no way for them to communicate faster than the speed of light. So when entangled particles encounter other particles, the entanglement ends. Yes, that is correct. Or because that is like a measurement. Would entanglement have saved Schrodinger's cat? That's funny. Schrodinger's cat is I was gonna put a cartoon of it. I decided not to, but that's another thought experiment for everyone. So Schrodinger's cat thing is where you have a cat in a box and there's a radioactive source, and if the radioactive thing decays, then some Rube Goldberg thing where it opens up some poison gas. So Schrodinger said, because of the quantum mechanics of radioactive decay, there's a certain uncertainty of when it will actually decay, that in that box you have a superposition of a live and a dead cat. until you open the box and see what you have, making a measurement. Um, it's an interesting thought experiment, but I think a cat's too big to really say it has a wave function. Um, Following up on last week, how do you modulate the frequency of the quartz crystal in atomic clock? That is an excellent question, and I'm glad you asked because that is something I neglected to explain. If you remember, it's the temperature. The temperature of the quartz crystal has to be stabilized. And as the temperature changes, the resonant frequency changes. So that's how you can tune your quartz resonator, is by the temperature of it. I'll give time for some more questions. And then we can briefly go over for those who are interested, the magnetometry stuff I didn't quite get to a couple weeks ago. And that's actually related to the work I do. I work on magnetometers. So I work with artificial atoms to develop magnetometers. So these are we got to hear, these are the two leading candidates. So what's an artificial atom? In this context, it's a point defect in a crystal that has energy levels. So what you can do, and here's a great example, you shine green light and it fluoresces red light. This is a piece of diamond that has nitrogen, lots of nitrogen vacancies. So what you see is going on here, this is like a unit cell in diamond. You knocked out one of the carbons, that's the vacancy. And then in these little gaps between the carbons, you put a nitrogen. The single vacancy in silicon carbide, this is a unit cell of silicon carbide. You knock out one of the silicon atoms, and now you have these dangling electrons from all your carbons. And so those dangling things kind of form an artificial atom. The spin of the nitrogen vacancy is 1. The spin is 3/2, which makes it interesting, very interesting for the silicon vacancy and silicon carbide. And so you have the ground state and the excited state. And so then when you pump with a certain color of light, and here you have a beam splitter that reflects higher, shorter wavelength light, higher energy, but it transmits longer wavelength. So here we're pumping with green light, a piece of diamond. Over here, that's a lens to focus in on it. And then it's emitting the red light. Here's some figures of merit. So with diamond, there's hundreds of defects. But maybe 3 or 4 are interesting. And it's because they have these properties where through optically pumping, you can spin polarize. So in the case of diamond, when you optically pump, you polarize it into the spin 1 state instead of being in the spin 0 state. The radiative lifetime. So how long, once you excite it, does it take for it to emit a photon? And it's like nanoseconds. And then a good fluorescence count rate. So you want it to be bright. These things we'll get to in a second. So I think I had enough time to talk about this article, but I'll briefly talk about it again. Here they took a piece of diamond and they decreased the amount of irradiation they did to the diamond till it was so low that they could see single defects. So this is a single nitrogen vacancy. And here they took a line scan across it to see how big that single defect was. And this is the fluorescing light from that single vacancy. This feature here is the zero phonon line. So if you were to cool the sample to say like 1 Kelvin, all of your light would be there. This light is redshifted or longer wavelength because of interaction with the crystal lattice. So optically detected magnetic resonance. I'm going to go back a couple of slides. No, I'm going to go forward a slide. So here we talked about how it emits red light and it's spin 1. Well, at 2.87 gigahertz, you drive transitions between the m equals 0 and the m equals plus or minus 1 spin states. And so what you can do is you can you're looking at the fluorescence of the light and you're applying microwave frequencies to your defects. And then once you get to a resonant frequency, you'll see a change in the fluorescence because one of these transitions will be brighter than the other. And what was very interesting, so this was like the first paper on these kinds of artificial atoms. So that's like 20 years. Yeah, 20 years ago. That when they looked at the whole collection of defects they made, they saw these 2 little humps. And then they started looking at individual defects. And they saw that some of them had the 2 humps, but some of them had 1 single hump. And this splitting has to do with the influence of the crystal. If the crystal's strained, then it splits the transition. If it's not strained, then you see how it's degenerate. So that was a really huge result. That was a really exciting result because instead of looking, this is where people were at before, but these folks, Gruber et al., figured out how to isolate and look at a single defect. And that way you can understand the fundamental properties of that defect. So I'm saying all this stuff. What in the world does it have to do with magnetometry? I'll explain. When you apply a magnetic field, that 2.87 gigahertz becomes different frequencies. So this is exciting. By measuring a frequency of an atomic transition, you can measure magnetic field. And as if you saw with all the atomic clock stuff, if there's one thing we know how to measure, it's time and frequency. So your typical magnetometer, you're going to use a voltage to measure magnetic field, whereas here you're using a frequency. So it's a much more well-defined, and it's rooted in more fundamental physics because what you're measuring is the response of these spin states to magnetic field. And there was a nice demonstration of using that to measure the neural activity of a worm. 2017, that's when it was done. And so there you have your piece of diamond, you have your green laser light, and here they're collecting the red fluorescence, and you got this stuff to do with the worm, and you have your big magnet. And sure enough, that's a very good question. So there's a question, does this measure the absolute value of the field? Yes, because with the squid magnetometer, if you remember, you can't use that as a calibrated you can't use, that measures changes of magnetic flux very well. So this is measuring the absolute field, and it's a fundamental measurement. So that means it's not something where you would necessarily need to have calibrated. It itself is something you could use to calibrate other magnetometers. And so by using it as a magnetometer, now you have a calibrated technique. Yeah, no, it's exciting. I mean, I don't know if you had a chance to see the Wired article, how Lockheed's trying to use it for a navigation device. But there's a lot of potential. That's why I'm working on it. Because I think it has promise. I think it has a lot of promise. Um, and so they would stimulate the worm on different sides, and this is the expected signal from that side versus that side. And sure enough, they were able to measure the response of the worm. Um, I was really excited when I first read the article a few years back, but when I was reading the article for this class to get ready, I realized that each of these plots was an average of 1,500 samples. So that kind of made me less impressed with the result. Though, I mean, who am I to criticize? I haven't done anything like this. Um, and that was it. So, yeah, I covered that stuff a little bit better. Thank you all for being interested enough to spend your time. I appreciate that. Bye.